get right into it. We kind of have probably just enough time to get to where we need to get by Christmas time. We got a couple quizzes yet to do, and an extra credit opportunity. Now, the extra credit opportunity will be the day, our last day before Christmas. It's an early dismissal day, and it's a tradition that we do this, and I call them the calculus carols. So now it's going to be interesting with a class of only 8. It may not take us very long to do these, and maybe, I don't know, maybe none of you will want to do this, but what we've traditionally done, and I will show you some examples from other years because I record them. And you can take some Christmas carol, or if you feel like you can't sing, trust me, we've had plenty of people who can't sing. You're not being graded on your singing ability. Or if you want to do like a Christmas poem like people have done, 'twas the night before the calc test. In other words, the idea is to take some Christmas poem or carol or something and put your own words to it, okay? Having something to do with calculus or this class or whatever. Now there are things out there on the internet. There are examples of those kind of things. I've looked at most of those that are out there. So I would rather you not just copy what somebody else has done, but have something original, some original lyrics. I mean, you can obviously copy different songs that people have done, whatever. But have original lyrics, something more to do with our class, whatever. And if you do that, then get up and do it in front of the class. You get some bonus points. So usually what I've done, if you do it by yourself, it's maybe 6 bonus points. If you do it in a group, you want to do it with a partner, 3 or 4 of you, whatever, you could get 3 or 4 bonus points. Probably no more than that. I mean, some people said, what if I do like 3 of them? Well, it's usually just a little bit. So, is it worth it? Well, it's kind of up to you. But it's just a fun opportunity to do that, whatever. So that is going to be kind of the last day. We'll wrap up. The day before that, we'll do a quiz, or a quiz, our last quiz. So we'll probably spend some time that day going over those as well. Anyway, so that's coming up. Next Tuesday, and you might have heard some discussion on the video about this, the gateway test. Okay, if you heard me talking about that, the gateway test. So next Tuesday, we will be taking a 10-question test over doing derivatives, just finding derivatives, y equals this, and then you do the derivative of it, okay? And you have to get 8 out of 10 of those right to pass. Now, you can, now I say to pass, I'm thinking of changing it just a little bit, that if you don't get 8 out of 10, I used to require you to keep doing it until you pass, until you got 8 out of 10. Because really that's the best option, because if you can't get 8 out of 10, it's going to haunt you later on when you can't do the derivatives, when we need to be able to do derivatives. Okay? But I am reconsidering letting you just take what you get. So if you get 4 out of 10, that's a 40%. So it's going to go as a 30-point grade. So that'd be 12 out of 30. That'd be a 12 out of 30 grade, which you probably wouldn't want. If you get 7 out of 10, you might say, 70, 21 out of 30, that's not going to change my grade much, or maybe it won't change it at all. I'll just go with that. Okay? It's a little harder to make them up because I'm not as available when we get, and we don't have the math office you can go to. So if you're going to take another, so you can, though, you're going to have the option to keep taking. If you get 8 out of 10 or better, the first time you get 30 out of 30 in the grade book. If you take it again, and I'll give you 2 attempts after that. Now it has to be outside of class after that. You take it one of the next 2 times, if you get 8 out of 10, you could get like a 27 out of 30, or maybe even I'll make it a 28 out of 30, which is still an A. That's in the 90s somewhere. Okay? And so you get really 3 attempts to get an A. either 30 out of 30 or maybe a 27 or 20 out of 30. Okay, after that, then you're going to kind of run out of time coming with Christmas probably, and then the best score you get is probably about an 80. Well, at that point, if you've gotten a 7 out of 10, well, that's only a 70%. So, it might be worth taking it the 4th and the 5th time. If you pass it one of those times, I'll give you usually a 24 out of 30, which is an 80, right? And if you don't, at that point, if you've gotten a 7, let's say you've gotten 70, then that's probably the score you have to take. You're going to have to make them up before school, probably come in early before school, or come after school, or possibly during my lunchtime, during first lunch, which is, if you're a senior, I guess, no, when's senior lunch? When's junior lunch? Last lunch? And senior is the middle. So you could possibly come in on one of those during my Bearcat time. Also, the seniors, don't let me forget, you guys got to leave just a little early because you got those speakers, right? We got those speakers. And yeah, we do go to lunch or Bearcat time right after this. So you guys need to leave at 5 till, so you can go to the speaker. You can just leave your bags. You can just leave your bags in here and then come back and get them after lunch or after the speaker or what. Well, I'm trying to think. My group goes to the speaker the last one, so I might not be in here, but you could come get it afterwards, whatever. After the speaker before you go to Bearcat time, maybe. Or lunch, or I don't know, somehow. All right, here we go. So these were the 2 new rules. This is probably the version that I will talk about most of the time. The red one's the U and the V. That's traditionally how we talk about it. This one was called the product rule. This one's called the quotient rule, right? And so you saw in the video where I did, x cubed times sine x, right? It'd sure be nice if x cubed sine x, it'd sure be nice if we could just do that derivative and make it be 3x squared cosine x, right? Sure be nice if that would be the case, but it's not. It's just not. Okay, it doesn't work. So whenever you've got a function times another function, you've got to take the derivative of the first, you leave the second one alone, plus you leave the first one alone, just like you take terms. You just take terms, right? The derivative of one, leave the other one alone. It's a plus. Now, it doesn't matter what order you do it, but I think it's a good habit to get into, to do the u prime, do the derivative of the first one, because when you go down here to the quotient rule, you have to do it that way. You have to do the derivative of the top, and then the bottom left alone, and then minus, and then the top left alone, and the derivative of the bottom, and then all over the bottom square, right? You have to do it that order because of the minus sign, so I think it's a good habit to do the product rule in that order. Okay, I like to avoid the product rule at all costs. If you want, if I don't remember on the video if I talked about this, if I have x cubed over 4, here's the problem. Some people start thinking about that as a quotient rule. Now that you've learned the quotient rule, people think of that as a quotient rule. The problem with that is it's way more work than it needs to be. Okay, if I have just a constant down here, I'm going to write that as 1/4 x cubed, and I'm not going to do a quotient rule. Okay? Only do a quotient rule if you have x's on top, right? If you have some x's on top and you have some x's on the bottom. It's the only time you want to do that. And to be honest, sometimes you don't even want to do that. If I have this, am I going to do a quotient rule on that? What am I going to do? I'm going to split it up. That's going to be x squared plus x. And then the derivative of that's going to be 2x plus 1, right? There's no, now, if you did a quotient rule on that, it would work. If you did a quotient rule on that, it would work. The problem is, when you go to do the derivative of the bottom, which you have to do right there, what's the derivative of the bottom? 0. And then that wipes that out. And people screw that up all the time. They forget that the derivative of 4 there would be 0, and they put a 4, and then it messes everything up. So it would work to do a quotient rule, but it's just unnecessary, and it leads to all kinds of bad things. So, and if I have 4 over x cubed, I'm not going to do a quotient rule, right? I'm going to write that 4x to the negative 3. Right? I'm not going to do a quotient rule on this. I'm not going to do a quotient rule on this. I'm not going to do a quotient rule here because I can simplify that. Right? So you don't, some people say, well, heck, you never have to do a quotient rule because anytime you're dividing, you can bring the bottom one up as a times, right? Like a reciprocal, but that leads to issues sometimes too. So sometimes, you get sine x over x cubed, just suck it up and do a quotient rule. That's you got to do a quotient rule. There's just no, no way around it, right? So I try to avoid it if I can, but sometimes you just can't. All right, so I've got some of the homework problems here. I don't know, let's go through this, and if there are some other ones you have issues with, we can talk about it. But this was an example. So what they told you on 11, exactly what I was just saying. They're wanting you to do it both ways. So like I was just saying, there's going to be some, you wouldn't want to do a quotient rule on this, but it would work if you did. So they're trying to show you that, okay, on this one, I would normally not do a product rule on this, right? On this one, I would multiply, I would add those powers together, right? 3, 6 plus 2, 6 is 5, 6. And then I would do the derivative, and I'd bring the 5, 6 down, and I would get that. That's what I would do most if I was doing that problem. But if I want to do the product rule, it'll work. So derivative of the first times that one left alone, plus the first one left alone times the derivative of this one. Bring the 1/3 down, drop that by 1, negative 2/3. Now, if we do this, we could add these powers together. That'd be negative 3, 6 plus 2, 6, so that's negative 1/6. Here we would have 3, 6 plus negative 4, 6, so that's also negative 1/6. When you've got like powers, that's like terms, so I can add 1/2 plus 1/3, which is 5, 6, and I do get the same answer, but why in the world would you want to do all that? Okay, it works, but you wouldn't want to necessarily do all that. So that's what those problems were about. Okay, 43. 43, you were supposed to find this. Now, I'm not going to have you do this on that gateway test we were just talking about, but we want the whole reason. Think about why we're doing this, right? What is chapter 3 about? Chapter 3, you notice on the assignment sheet, everybody got that too, by the way, right? Everybody got this assignment sheet. I passed it everybody. Really short little chapter, right, compared to the last chapter. Well, all it is, the whole chapter is just how to do derivatives, right? And to be honest, maybe I should pull that up here right now. I've attached this on today's homework. This was in the video. You saw this in the video. Don't worry about these U's down here. We're going to talk about those later today, okay? But this is attached on today's, on our website, so you'll have this, a copy of this. This is all of our derivative rules. Now, we don't have them all yet, but we recognize some, the plus minus, if you got a K out in front. I didn't put the one about when you have a number on the inside. You're going to see why today. Here's our product rule that you learned right here yesterday. Here's our quotient rule that you learned yesterday, okay? This is the new one we're going to learn today, okay? Here is all of our power rule. We bring the power down. E to the U is its own derivative. B to the U, we tack on that. Natural logs, 1 over, of course, we called it 1 over x. You'll see why I put u's there. Just hold that. Today, we had that rule already. Sine and cosine we had. I think I told you guys this one. Tangent, derivative of secant squared. We're going to have to know the rest of the trig ones now. We don't run into those very often. If you know sine, cosine, and tangent, you're in pretty good shape. But every once in a while, these do pop up. So cotangent, secant, and cosecant. The little asterisk by them, I mean, these are probably ones you're going to have to spend a little time studying before next Tuesday when we do our gateway test. And then I think tomorrow or maybe on Friday we'll be doing the inverse trig one. So we don't have very many rules left to do, right? It's a matter between now and Tuesday practicing, a lot of practice. I got all kinds of websites with multiple places to practice. And, you know, I don't know. I look at our quiz from last time. We had some really good scores, and we had some not as good. And I didn't get a lot of people coming in and asking questions before that last quiz, right? And I remember looking at your homework sometimes, and I was saying, you know, you're supposed to be showing more work than this. Your homework was a little lacking sometimes. You know, I'm not sure how much time was being always put into this and how much effort coming to ask me and so forth and so on. So you've got all kinds of opportunities to practice before this gateway test next Tuesday. You know, you're going to need to make a commitment to put some time into that, okay? All right, so back to this one. So when we get to that, so basically chapter 3 is just about learning these derivative rules, because as we learned, think about our last quiz, finding local max min, finding global max min, finding inflection point. It's all dependent on us being able to find f prime, find f double prime. If we can't find the derivative equation, if we don't know these rules, we can't do anything. And the antiderivative is just those rules in reverse. So you got to know the derivative rules. Okay, all right. So here you've given this function here, and they want you to find h prime of 2 and h prime of 4. Now, I think Is there a graph that goes with this one? Number 43? Yeah, I think there was a graph that went with this one, and they gave you what, the F graph? They give you the F graph on this one, okay? So they don't give you an equation. Now, that's not going to be our gateway test, but we need to still be able to do these things, right? We're not just totally focused on next Tuesday's test, right? We've got other stuff going on here as well. So before you can find h prime of 2, you need to find h prime of x, right? You need h prime of x. So h prime of x would be this, be the product rule. Two functions being multiplied together, we got to do the product rule. So derivative of the first, 2x, f left alone, plus x squared left alone, derivative of the second, which is f prime. Now we put a 2 in everywhere we see an x, okay? So we put a 2 there, put a 2 there, put a 2 there, put a 2 there. So we look at our graph for f of 2, we go over here to 2, we go down to the y value, it's negative 4. Okay, so this value here is negative 4. We go here on the f graph, we look at the slope at 2, the slope is 0 right there at 2. So we get 4 times negative 4, which is that, we get 4 times 0, which is that, and we get negative 16, and then you do the same thing for the 4. Now the difference is, on 4, when you do f prime of 4, you got to kind of estimate that slope. You got to kind of do a tangent line thing there. And I called it 4. I called it 4. Okay? You might have something a little different than that. And then f of 4, of course, the y value is 0. So that wipes all that out. 16 times 4 is approximately 64. Okay? All right. Next one. You were supposed to find, what am I doing now? This must be 45. This must be 45. Because they're asking us, is h concave up at negative 1/2? Well, what do you need for did we have to do 45? Was that one that we did? Yeah. So, is h concave up at negative 0.5? So for 44, it says show that h has a stationary port x equals 0. You just plug a 0 into this, right? You plug a 0 into this, you plug a 0 into this, what do you get? You get h prime is 0, right? So it's a stationary port, so that's easy. So 45 is h concave up. What do you need to tell concave up? Second derivative. So here's the first derivative. Now we've got to do two product rules. So we got to do the product rule on this one. So derivative of 2x. Notice how I put that dot there? Because I want you to treat this as the u and this is the v. That 2, you might say to yourself, well, wait a minute, 2 times x, that's a product rule. Nah, 2's just a number, so we treat that different. Treat the 2x as one thing. The 2x is one thing, so that's your u. And then the f of x is your v. Okay? So derivative of 2x is 2. Leave that alone. 2x left alone, and then derivative of f is f prime. Plus, this derivative is 2x, leave that alone, then leave the x squared alone and derivative of f prime, which is f double prime. So that's a lot of stuff. Now, we want to put in a negative 0.5. So we put a negative 0.5 in for every single x. Okay? Every single x. Okay? Well, I'm going to go to my f graph and look at negative 0.5. Well, negative 0.5, it looks like it's about 2. So I'm going to call that 2, what did I say? No, it looks like I called it 2.5. Looks like I called it 2.5. You might call it 2, it's kind of roughly. I called it 2.5. Okay? And looks like I called this slope here negative 4. If you go to negative 0.5 and do the slope, I called that negative 4. Okay, and I got another one of those right here. Okay? So I've got that there twice. And then I needed f double prime of negative 0.5. How do I look at the f graph and get negative? How do I get f double prime? Notice I left it blank here. What do you think? How do I look at the f graph? Which looks like this. How do I get the second derivative right there? You don't. You don't. Well, what do I know about f double prime there? Huh? No, I know f is concave up. So what's f double prime? Positive. So I don't know what F double prime is right there, but I do know it's positive. Now, I hope that's going to be enough. Might not be, but I hope that's going to be enough. Because remember, what's my question? Is H concave up? That's my question, right? That's my question. Is H concave up? Now, F is concave up the whole time, right? F's concave up. But the question is H concave up? Well, how do we know if H is concave up? If H double prime is positive. So I don't really need to know what H double prime is. I just need to know if it's positive, right? Well, look what I get right here. What's 2 times 2.5? Positive. What's negative 1 times negative 4? Positive. What's negative 1 times negative 4? Positive. Negative 0.5 squared is positive times a positive. What can you tell me about H double prime here? Positive. See, I went ahead and found those values. But I got 5 plus 4 plus 4 plus some positive. So therefore, since H double, then I would say this, since H double prime is positive, H is concave up. That's what you needed for 45. My guess is if I went around, I'm not even going to look, but if I went around in your papers, would I see all this written down, number 45? Or would I see like one little thing because you look in the back of the book and you weren't sure what to do, right? You've got to be able to do this. You've got to be able to write this stuff out. You've got to be willing to write it out. And if you don't know what you're doing, you need to be willing to come in and ask me about it, okay? 48 is the next one I want to talk about. Is M increasing at x equals 3? So if we're skipping over ones that you had questions about, then you need to be coming to talk to me about this. These are the ones that I thought were a little more challenging. Is M increasing at 3? Again, if M is increasing, means M prime is positive. So you got to ask yourself, what am I trying to find? If they want to know if M is increasing, they're asking me to find if M prime is positive. So before I can find M prime of 3, I need M prime of x. So M prime of x is going to need a quotient rule. There's just no way around it. Yeah, I could bring this up as a negative 1 power, but that's something we can't even handle right now, to be honest with you. We will be able to in a little while, but not right now. Okay, so derivative at the top, f prime. Leave the bottom alone. Use a lot of parentheses when you do quotient rule especially. You've got to put that x squared plus 1 in parentheses. And especially over here it's important because of the minus sign. We miss, my calc students in the past, and no matter how often I warn you, because of this minus sign, if you don't use parentheses properly, you're going to mess things up over there. Okay, you've got to be careful. All right, so then we do the top left alone, and then derivative of the bottom, just 2x. Now, if there had been a plus there, parentheses have been really important. The way it is, not as important. But if that had been 2x plus something, parentheses have been really important. All right, and then the bottom squared. There's your quotient rule. Okay, now we just got to start plugging in a 3. So we plug a 3 there, 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 we plug a 3 there. Okay, so there I get it. Okay, f prime of 3. So we go to 3, we look at the slope, I called it 2. Put a 3 there, we get 10. F of 3, we go to 3, look at the f value, it's negative 3. And then 2 times 3 is 6. So here I get 20 minus a negative 18, it'd be plus 18. Down on the bottom, I get 10 squared, which is 100. Clearly, that number is positive. So m prime of 3 is positive. So therefore, m is increasing. That's what I'm doing. So this is just a chart question using the quotient rule. Okay? 79. Okay? 79 says, we have this function. At what value of x does f have its max value, its min value, and an inflection point? Now, what do they want when they're talking about the max value? Global max. What do they want, the x value or the y value? They want the y value, right? Global max min. A few of you had an issue. I don't know if there's anybody in here, but a few people on the quiz had that issue on the global max min problem. They wanted the y value, not the x value. What is the max and min value? We got the endpoints, so our list of candidates is our endpoints. And where else do we look for global max min? At the endpoints and stationary points, where the derivative is 0. So we're going to plug into our original, we're going to plug in 0, we're going to plug in pi, because those are our endpoints, and we're going to see where the derivative is 0. So here's where we really need then to do the solving part of this. So far, we've been just doing the derivative and plugging numbers in. Now we need to do the derivative and set it equal to 0. We need to find our stationary point. So this is clearly a product rule. Two functions multiplied together. So we're going to take e to the x times cosine x. So derivative of e to the x just itself, cosine left alone, plus e to the x left alone. Derivative of cosine is negative sign, but put it here. I see people do this. They go, oh, okay, e to the x, and then the derivative of cosine is negative sign. Now, what does that look like to you? Doesn't that look like subtraction? Is it supposed to be subtraction? No, it's supposed to be e to the x times negative sine x. Don't put the negative on the sign there. Stick it, make it a times, stick it around there in front on that term. It's like having AB, negative AB, and writing it A negative B. Why would you write A negative B? You'd make it negative AB, right? You put the negative out front. It's like a coefficient, okay? So make sure you do that. Now, where does that equal 0? Well, first step would be to factor out e to the x. This is why we did that solving equations worksheet weeks ago. Problem like this. We got to factor out e to the x. This would be a no calculator problem. I really think, yeah, it could be a calculator problem, but it could be a no calculator problem. So, where does this equal 0? Or where does this equal 0? Well, let's treat this one first. Where does e to the x equal 0? No, because e to the 1 would be e. Huh? Never will. Now, you could do the log of both sides. One of the things we talked about is then do the log of both sides. Okay, that gives you x times ln e. X equals ln 0. What's ln 0? That's ln. It's ln. There is no ln 0. There's no value of 0. Or you could just look at this and say, well, what's the e to the x graph look like? E to the x looks like that. Does it ever hit the x-axis? E to the x is never 0. So we just ignore that. Okay? Never. So where does cosine equal sine? Now, this is where it gets tricky. And I'll admit this would be a pretty tough trig, but it could happen, right? It could happen on the AP test for sure. So how would we finish that? What I would do is, I think the best way to do it is to add sine over to the other side and just stop right there. Now, some people would divide by cosine and they get tangent equals 1, but you got to be careful whenever you divide by an x. I'd rather just look at this. Between 0 and pi, right? Between 0 and pi, where does cosine equal sine? Right there at pi over 4. They're both root 2 over 2. Not over here though, right? Because over here cosine's negative and sine is positive. Now if this said 0 to 2 pi, we'd have another one down here where they're both negative. But cosine equals sine when x is pi over 4. That's the only time between 0 and pi. So there's our stationary point. And now we've got to now plug that back into the original to find it. Okay? And, oops. So we put 0 in, e to the 0 is 1, cosine of 0 is 1, 1 times 1 is 1. Put in pi, e to the pi, what's cosine pi? Negative 1? Cosine pi is negative 1. So that'd be negative e to the pi, whatever the world that number is. It's 2.7 raised to the 3.14, right? Okay? And then what's pi force? This would be e to the pi force. And then what's cosine pi force? We said that was root 2 over 2. So that'd be e to the pi force times root 2 over 2. Now let's think about this. This would be 2.71 raised to something. This is like 0.7. You know, the question is that bigger one? This is where it would get a little tricky if this was a no calculator. Clearly, this is your minimum, right? That's your minimum right there because it's negative, okay? And then the question would be which one of these is a max, right? And that's where it might be a calculator for that. It's not very obvious which one is the max. Okay, and I'm gonna skip part C just because of time. Where does it have an inflection point? So what would we need to do? We would have to do the derivative of this guy right here, which would be 2 product rules would be needed. Now what you would find is some terms would combine and so forth, and you would have to set that equal to 0 and solve. It would be a very similar situation as this. But then you would have to do a number line. For an inflection point, you would do a number line kind of thing and see what you get. Okay, but I don't want, I mean, that's stuff we've done. The solving part might be a little tricky, but, right, we've done those things. You understand what you need to do. You need to do the second derivative, set it equal to 0, go from there. Okay? All right. So get your notes out and let's move on along here. And I'm not going to take time to get the hats and whatnot here. I'll just type it into mine. But we want to do this problem right here. Sine of x cubed. All right? Because we've talked about what to do if you have a 3x inside there. What's the derivative of sine 3x? We kick out a 3. Now, why did we kick out a 3? Well, we said because that 3 compressed the graph, right? That 3 compressed the graph, which moved the slopes inward, all the y values that moved inward, and then it made the slopes 3 times as much because you compress it. So you had to kick out that 3. But what we don't know, what we haven't talked about, is what do you do when you have some other function inside there? I mean, so we've talked about if you just have a plain x inside, and then a number times it, you just kick out that number. But there's functions like this, right? There's functions where you have a function inside of a function. Those are called composite functions. What we're talking about is this kind of a thing. We're talking about f of g of x, which, by the way, your book kind of drives me nuts because I don't know, I just hate this notation. It just seems goofy. They sometimes write f of g of x, and I call it fog notation, okay? Every time I see that, I think it says fog, okay? But sometimes they'll use that for f of g of x. So if you see that, just understand that's what it means, okay? All right, so what do we do when we have a function inside of a function? Think about it. This is the last thing we need, really. I mean, except those inverse trig we were talking about, those functions. There's another little thing we got to talk about tomorrow. But really, we talk about adding functions together, just do their derivatives individually. Subtracting functions, you just do their individual derivatives. If you times two functions, we got a product rule. If you divide two functions, we got a quotient rule. So the only thing left is what happens when you put a function in a function, like this. Okay, well, if we go to our calculators and we go and ask our calculator to do it for us, which the magic of our calculators, it will just do this for us. So I'm just going to do the sine. Maybe you've done it already. Oops, and then that would be bad. Okay, go there. So I'll just do the sine of x to the third. And what did it do? So it left the inside alone, which I've been telling you we're always going to do, right? I always said whatever's on the inside is going to stay on the inside. We did the derivative, right? And it did that. And it kicked out the derivative of the inside. Whatever was on the inside just did the derivative of it, kicked it out. Now, when you think about it, isn't that kind of what we were doing before? Remember when we said kick out the 3? Well, what's the derivative of 3x? 3. If we have a plain old x to the first and we have a number in front of it, we said kick out the number. Wasn't that the derivative of, right? If you have a number times a plain old x, the derivative of that is going to be, and if we had a 2x plus 1, what's the derivative of 2x plus 1 if that was on the inside? Just 2, because the 1 will go away. So if we had a plain old x, even if there was something added on, we just kicked out whatever number was in front of the x. Well, that's the derivative of that. So I didn't tell you that's what we were doing, because it didn't make sense why necessarily we were doing that. I like the compression idea, okay? But it turns out that it's just a special case of this, okay? And so what we do, and so here's how, and I think I wrote it down, yeah, over here. So what the calculator did for you is it did your regular cosine, which is the outer function. If you talk about composite functions, we usually talk about inside and outside, the inside function, the outside function. So it did the derivative of the outer function, which was cosine. It left the inner function alone, and then it times by the derivative of the inside. Now, usually, when I write this, I tack it on after, but a lot of times, when I write my final answer, it makes sense to bring it back around front. Not always. I could have just left it over here, that's fine. But if there had been a 4 setting here, right? If there had been a 4 setting here on the outside, then I'd want to bring that 3 with the 4 and make it 12, right? That would be simplified to me. Okay? All right, so for your notes, here's what the chain rule says. Okay? The chain rule basically is this. If you have f of g of x, you've got some function inside of another function, it's really a 3-step process. It's a 3-step process. If you look at it, it's derivative of the outside, which is f prime. You leave the inside alone, which is the g of x. And then you times by the derivative of the inside, which is the g prime. That is called the chain rule. Now, why the word chain? I've seen why they call it the chain rule. To me, it doesn't make a lot of sense. It's like the gears and chains. I don't see the connection, so I'm not going to worry about it. But it is called the chain rule. The most common rule we use in any derivative, a lot of times inside of a product rule, you have to do a chain rule. Right? Inside of a quotient, we have to do a chain rule, because sometimes you have a function times another function, but those functions that are being times have stuff on the inside. We don't often work with just sine x, or just x squared, or just e to the x. We work with sine of some stuff. You'll hear me say that a lot, right? We have e raised to some stuff. We have some stuff squared, right? So we don't often have just x squared, sine x, e to the x, right? All right, here's what I wrote out in words. So again, what I just said is when you're doing the chain rule, and you don't have to think to yourself, oh, I'm doing the chain rule. You don't, right? You don't have to think about the chain rule. You just say, oh, there's some stuff on the inside. Okay, what am I going to do? I got to do the derivative of the outside. I got to leave the inside alone. And then I have to multiply by the derivative of the inside. Multiply by the derivative of the inside. Not add, multiply by the derivative of the inside. Yes?
So if you add like e raised to the ex plus 1,
right,
would this apply to that? And
sure.
You would pull 3 down.
Well, yeah, because that's the derivative of 3x plus 1. So in other words, yeah, what constitutes an inside? Right. That 3x plus 1 is considered the inside of the e function. Yes, that's considered the inside of the e function. Very good. Because you're right. When you have sine of 3x plus 1, it's clear that 3x plus 1 is the inside. When you have 3x plus 1 squared, it's pretty clear that 3x plus 1 is the inside. When you just have e to the 3x plus 1, a lot of times they wouldn't put parentheses around that. That is the inside of the function, right? ln of 3x plus 1. 3x plus 1 is the inside of that function. So a lot of times we call this, I just say this is sine. So when you'll hear me say, what's the derivative of sine? What I really mean is the derivative of sine of some stuff is cosine of that stuff. And then times the derivative of the inside, derivative of the stuff. So you kick out a 3. Right? Or if that was a 3x squared, you kick out a 6x, right? The derivative of the inside. So those are our main functions, right? I mean, we can't, we got power, we got trig, we got log, we got exponential, right? Those are now, I think I'm leaving it in. But yes, that's the inside. So here, e's the outer function, sine's the outer function, squaring is the outer function here.
So does it apply the same if e is just a number?
What do you mean if e is just a number?
If e's 4.
Oh, if you have 4 to the 3x plus 1?
Yeah.
Yeah. The rule now, remember, is 4 to the x. The derivative is 4 to the x. So this would be 4 to the 3x plus 1 times ln4, remember, and then times, let's pretend that was 3x squared. So this would be 4 to the 3x squared plus 1. The derivative would be 4 to the 3x squared plus 1 times ln4, because that's that rule, times the derivative of the inside. What's the derivative of that? 6x. That would be the derivative right there. That would be the derivative of this thing right here. Right? Because the rule says, now, I'll tell you what, this would be a good time to go back to that, to this page right here. Okay? So, why did I put these U's here? Okay? Now, you don't have to copy this down because you're going to have a copy online. But look at this. So, why did I write, notice here it still says with respect to x, right? So, what I've done is I said, just let U be a bunch of x's, right? So, what this rule is now is like 3x plus 1 to the nth power, or sine x to the nth power, or e to the x to the nth power, right? The U just represents a mess of x's. So if I've got some stuff raised to the nth power, what I do is I bring the n down, I leave the stuff alone, I drop the power by 1, and then I times by the derivative of the inside. What's the inside? It's the U. So the derivative of the inside is U prime. So we're always tacking on the U prime. So if I have E, just like you just asked, you have E raised to the 3x squared plus 1, it's E raised to the 3x squared plus 1 times the derivative of 3x squared plus 1, which is 6x, right? So what I've done here is I've put the chain rule into all of the rules. So if you have 4 raised to some stuff, then it's 4 raised to that stuff times ln 4 times the derivative of that stuff, which we just saw was 6x, right? We don't typically have just sine of x. We typically have sine of some stuff. So sine of some stuff, the rule is cosine of that stuff times the derivative of the inside. Make sense? So that's why I have all these u primes stuck out here, because that's how we want to think of those rules. So now when I talk about the rules, I'm not going to say what's the derivative of sine x. I'm going to say what's the derivative of sine? Cosine. Because I just understand it's going to be sine of some stuff, so the derivative is going to be cosine of the stuff times the derivative of the stuff, derivative of the inside. Okay? So that is, so the chain rule is just kind of embedded into our regular rules. Okay, let's do some quick examples here. We got enough time left here to just do some quick examples. All right, just write down real quick what you think the derivative of that would be. If you guys have to be a little late, if your speed point will be late, but we'll be in. Might not get in the front though. All right, so what do? What is the outer function here? What is the function? What is the rule we're doing here? This is the power rule is what we're doing here, right? We got some stuff raised to the 8th power. So the rule is we do what? We bring the 8 down. We leave the inside alone to the 7th. It's amazing how many times we forget to put that 7 on there, because we're thinking about all the stuff on the inside. You know what I do sometimes is I'll go 8 parentheses to the 7th, and then I'll go put the stuff in the parentheses, just so I don't forget that 7. So we bring the 8 down, leave the inside alone, 7th power, times. Now, here's another thing I often do. I often put a blank set of parentheses here, because now I'm doing the u prime, right? Now I'm doing the derivative of the inside. Well, the derivative of the inside is messy enough itself. As a matter of fact, look at e to the 2x. It has its own stuff on the inside. But listen, we've done e to the 2x enough, haven't we? What's the derivative of e to the 2x? 2e to the 2x, right? You're just going to kick out a 2. So you don't have to think to yourself, oh, we got the chain rule and the derivative of the inside. It's just, you know that e to the 2x is 2e to the 2x. Because we've been doing it, right? So we've got that. Plus, Derivative of 3x is 3. Let me tell you, if you wrote this, that is wrong. And if you write that on the gateway test, you will miss that problem. And I don't care how big you put this dot. Some people think if they make that dot a lot bigger, then that makes it better. Why is that wrong? Because please excuse my dear Aunt Sally says multiplication takes precedence over addition, and all you're doing is multiplying by the 2e to the 2x. You are not multiplying by the whole thing, right? You've got to put that in parentheses. You're doing the derivative of the outside, leave the inside alone, and then that has to be times the derivative of the inside. Now, sometimes it doesn't matter. Sometimes the derivative of the inside is just one thing, like this 6x. So I didn't have to put it in parentheses. It was just this thing times that thing, and I didn't have to put the 6x in parentheses, okay? But a lot of times, it's got a plus or minus with it. You've got to put, so what I often do, like I said, is I'll write this, oh, now I got to do the derivative inside. I'll just put a big set of blank parentheses. Now I'll do the derivative inside, and I'll stick it in there. Now, if I don't need them, no big deal. On this one back here, if I'd have had the 6x in parentheses, nothing hurt. Okay? All right, do that one. ln x raised to the 5th power. Don't look up here now. Don't look up here. I'm going to put the answer up, so don't look up here unless you want to cheat. Don't be a cheater. Okay, the answer's up there anytime you're ready to look. Agree with that? The outside function is 5th power. So we're going to do the power rule. So we bring the 5 down. We leave the ln x alone to the 4th power. But then we got times by the derivative inside. The derivative of ln x is 1 over x. Now, could I put those together? It would just be rearranging. I can bring the 1 over x out in front, put it with the 5. It's not a bad idea. Probably looks better. But I'm not that concerned about that. If this would have been a 1/2 here, then I'd have been concerned about it. 1/2 times 5 is 5 halves. You need to put that together. So it's probably not a bad habit to get into to do that right there. Okay? All right. Try that one. 2 to the sine x. 2 to the sine x. Sure,
Good morning, and pardon the interruption. At the conclusion of this announcement, please release all seniors and sophomores in the following Bearcat time groups.
I'm going
Henning,
to put the answer up here, so don't look if you don't want to see it yet.
Johnson, Kreitzer, Linda McFadden, and Limmer. Thank you.
Okay, the answer's up there anytime you're ready to look. This is like the one Max asked about earlier, right? The rule is 2 raised to some stuff is an exponential. So 2 to the x, the rule is 2 to the x times ln 2. Well, this is 2 to some stuff. So it's 2 to that stuff. This is the inside. We leave it alone. Times the ln 2, but then we got to do the derivative of the stuff, derivative of the inside. The derivative of sine is cosine, and we would just leave it. Okay? Tangent squared. I'm just going to run out of time, so I'm just going to talk this through. Tangent squared. The reason I put this one up here is because people get messed up. What's the inside function here? No? Well, yeah. X is on the inside, but no. Listen. This is when I hate this shortcut notation. I hate this sine squared, tangent squared. I hate that notation because that's what this really means. What's the inside function? You guys are juniors. You still got plenty of time here. We got 5 minutes, but I'm going to let seniors go in a second. But look at that. What's the inside function then? Tangent's the inside function. What's the outside function? The square. So you're going to bring the 2 down. You're going to leave the tangent alone. tangent x to the first times, and then what did we say the derivative of tangent was? Secant squared, and this is just x, so it's just tangent x, so the derivative of tangent x is secant squared x, or you could put secant x quantity squared, I like better. Okay? Now don't write this one down or anything, but look at this last one. Okay? Again, the first thing you got to realize is that this is this, like that. So what's the outer function? The squared. So we're going to start this by doing the outer function. We're going to leave the inside alone to the first. Now, we have to multiply by that. Let me do it in blue. Well, it's got its own inside stuff, right? Well, that's okay. We just keep going. So now we're doing the blue. What's the derivative of this? Well, derivative of sine is cosine. We leave its inside alone times its inside 3x squared. Now, you've got this times this times this times this. The parentheses don't really matter. I can rearrange them. It's like A, B, C, D all times together. I can rearrange them. So the 2 and the 3 I should put together, make that 6x squared. Then I would have sine x cubed. Since its first power doesn't matter, cosine x cubed. There's your derivative right there.
So if we left it as the one in the red, is that okay?
No, this would not be okay because I want that 2 and that 3 to go together as a 6. All right, so your homework, look at this one. You got an inside that's going to need what rule? The quotient rule, right? All right, your homework is 3.2, the 3.2 homework questions. Okay, the 3.2 homework questions, which is on that sheet. Okay, so it's very much like yesterday's. You're going to have some with like tables, like we had there, where you have to plug in certain values and so forth. But I'll be here early in the morning. Okay, seniors, you guys can go to your speaker.
We can leave our bag.
Yeah, you can leave your bags here because you're supposed to. I think you're supposed to leave your bags. So, yeah, let's put them back there because of my Bearcat time.
Where's the speaker today?
I think it's business, marketing, information technology. Yeah, leave it.
Friday, we have the health sciences, and then next week, I think we have 3 more.
I think that's right. I know we have to have skilled and technical. Yeah, we have to have.
But then the blue one.
That's business.
Oh, the core academy. There's so many kids talking about that.
What's yellow? Yellow's business.
Yellow's business.
Blue's like skilled and technical.
No,
That's orange. That's where we're in skilled and technical right now.
Red is health science.
Oh, the ag and natural oh no, we had ag already.
Yeah.
And we had the fine and performing arts.
That's.
Oh, there's human science
Yeah.
education.
That's red.
Oh, that's red. Okay, human science.
No, it's not.
Well, that light blue is the.
Oh, no, it's health sciences.
Yeah, there's health sciences and there is like the education.
Human sciences.
Yeah.
That's the dark blue, right? The human sciences, the one
So
downstairs.
They're human
Yeah.
sciences, health sciences, and then skilled sciences.
All right. Oh, well, since you guys are still in here, I might just comment on this. So you think about those problems we had with the graph. So they're gonna ask you a question like, is H increasing at 2? Well, you want to find if H prime is positive. So you just write out H prime, which is that new rule, and you plug in the 2. So that's everything.
Clear now.